here. YouTube's. Subscribe to my TikTok. There's lots of epic pranks. We're gonna do this problem, the spring. Okay. It says a 5 kilogram disc is attached to a spring with a spring constant of 200 newtons per meter. So let's start labeling some information here. So this is 5 kilograms, this is the mass. Spring constant K is 200 newtons per meter. And so the natural length of the spring, so let's say initially the ball is here, was 1 meter. And so what's going to happen, I guess I kind of gave it away, but if you start spinning this thing around in a circle, what's the spring going to do? It's going to stretch out, right? There's different ways you can think about that. You could again think of that in terms of your centrifugal force, right? From the reference frame of the ball, he's being kind of pulled outward by that spinning. That would tend to stretch the spring. Or you could think from outside the reference frame, you could say, well, something has to exert a force on this ball to keep it in the circular path. Well, who's providing the force? The spring. What happens to the spring? What has to happen to the spring in order for it to produce that force? It has to stretch. So this says that it stretches out to once it hits its equilibrium. So it's really interesting is if you actually just started this thing, you might actually get some oscillation in the spring, which we'll study later. What happens when you take a spring and you disturb it and it oscillates back and forth. But anyway, this says we do it steadily enough that we work our way up to an equilibrium. And what's the radius? What's the length of the spring? 1.4 meters. Okay. So what should we do? What equation do you think we're going to write as just a starting point? Man, like if you cry every time. That's an epic gamer moment. Well done, Aaron. You're the man. F net equals MA. Okay, that's the equation we pretty much are always going to write. So, who is providing the force? Like, what am I going to replace this F net expression with? The spring force. Well, the spring force. So how much force does a spring provide? What's the formula for spring force? Okay, so our definition is the change in force over the change in length gives us K. So if we kind of rearrange that formula, we'd say that the force is K times the change in length, right? So what was the change in length? And I know it's a change in force, but what was the spring originally providing? Before it started moving, it was 0, right? So the change in force is the final force. Right? So this is going to be basically, or I can write like this, Kx, right? Kx being the displacement. Or the K is another way of writing delta L. That makes sense? Like x being the displacement, how much of the spring changed in length? M is m. And what's the acceleration? What do you replace the acceleration with if you're in a system that's yeah. So I'll tell you what the most common mistake that students make with these kind of questions is they replace this with mv squared over r. Because they go, oh, it's centripetal force, mv squared over r, but then you end up with an equation that's just like, it's like circular. So what you got to remember is use your force diagram or your physics knowledge to figure out which where is the net force coming from? Is it coming from a spring? Is it coming from normal force versus gravity? Is it coming from a string? Whatever. And then replace the A with V squared over R. So anyway, let's plug in everything we know. K was 200. X was 0.4. The mass was 5. The V, does it tell us the V? We're solving for V, right? Okay, makes sense. And the R, what is the R?
1.4.
It's 1.4, yes. Because that's another point of confusion. People, they go, is it 1? Is it 0.4? Or is it 1.4? Well, R represents the actual radius of the circular motion. So this is the radius at which it's rotating circularly. Let's solve this. So it's going to be this times this times this divided by this, all under a square root. What does that give us? Did anyone already get it? Kate, did you get it?
4.73.
Check your answers, guys. This is what Kate says.
That's what I got. Yeah. I don't know what you got it twice.
If you can't get from here to here, that's an issue. That's not good. It's fixable. We can certainly fix it, but you're in rough shape.
Caleb, you're in rough shape.
It's not to make you feel bad. It's just, it's just a heads up. Like that. That should be the easy part. That should be the easiest part of the question.
That's like, yeah.
Did you get them out of
That was
there?
like 2 days ago. When you figure out. The 164. Oh my. Oh. We've been doing that for years. You guys are the whole trigger. We was yelling about it in government for like, yeah. You made I did it wrong. I was like, everyone else suffered. I was like, how the hell did I do it wrong?
Do what wrong?
He's like, Caleb could not figure out to cross multiply in calculus 2 days ago. And then I tried to explain it to him, and he's like, that is wrong. And I was like, I just explained it to you. He's like, no, I'm right. I can't understand how you do that. I said, okay, just be a small brain.
Okay.
This will learn you to work here, so. Which one is this?
Okay. Number 20. Number 19 should follow pretty simply from what we just did. If you're confused, I would just go back 2 or 3 steps to where we set up the equation, and you should be good to go to generalize that formula. So, before we get into the quantities involved here, I want you to think about what would happen if you had this hump in like a track, and you rolled a ball really fast. It would leave the track, right? It would, at a certain speed, it would be going too fast, and it would leave the track. So this little collection of questions, I think there's 6 of them, or there's 5 of them, are basically going to try to quantify like how fast can this ball be going at the top of the ramp without flying off the ramp.
Why wouldn't you want to?
Why wouldn't you want?
Yeah.
Well, a lot of reasons. I mean, say you're in a car and you don't want to assuming you're not in like a rally car, you don't want to fly off the road.
Well, if you're in the air, aren't you using less gas?
True, you've saved the earth. Yeah, you pat yourself on the back. Here's a good question for you, and it's actually a few questions ahead, but we can discuss it briefly. Let's say you're on a road It's kind of like this. Here's your car. If you were going to hit the brakes and wanted to stop, you wanted to stop as quickly as possible, would you want to hit the brakes like at the top of a hill or at the bottom of a hill? What do you think? Which would be better? Say you're going to hit the brakes. Say, I don't know, here's I don't
No, that's when you hit
Bottom of the
gas and
hill,
jump
because you're gonna have-
Yeah.
just jump him, yeah. The question is, how would you generate the most stopping force? Theoretically, could you generate a lot of stopping force at the top of the hill or the bottom of the hill?
It would be the bottom because you're done accelerating.
Well, no, because
Assuming you're coming constant speed, you went 40 miles per hour, and you want to be able to hit the brakes and get as much stopping power as possible. Or even say, if you can imagine in your head this being a big turn, a turn that has like a hill in it, kind of a little bit harder to imagine, but can you get for your turning, to get as much friction as you can get for turning, would you want to initiate the turn at the top of the hill or the bottom of the hill? Anyway, we'll get to that. The answer is the bottom. The bottom, you're going to have more normal force. The bottom of the hill, the road is providing much more normal force to you. Your car is basically heavier at that moment. And if you're heavier, you can generate more friction force.
It's like the roller coaster.
Yeah. Exactly. So you'd want to hit the brakes when you're the heaviest. So I'm going to show you that here. So number 20 says there's a 3 kilogram ball, 3 kilograms, and he's sliding along a frictionless track, comes across a hump in the shape of a circular arc. So this is a circular arc with a radius of 2 meters. The ball is traveling 4 meters per second at this moment. What's the force exerted? Hello. Sure. Bye, Hannah. We'll miss you.
They'll be gone for 3 months like the last time.
Don't forget the Snapchatter. Almost forgot the Snapchatter. Oh, whoo! Those streaks would have been. Can you imagine all the streaks that would have been lost?
Yeah.
It would have been terrible.
Died too young.
Okay. So the question is, how much force does the track exert on the ball at this moment? How much force does the track exert on the ball, say when he's over here? Let's look at that one real quick. mg. So mg in this case would be what? 29.4 newtons. Okay. So how much normal force is there? 29.4 newtons. However, over here, it's different. How much gravity is there? 29.4, right? Newtons. But this vector, here, tell me if this makes sense. I already know, without doing any mathematics or calculation, that this vector has to be smaller than this vector. That is a physics inference. You can No, it's not. Has nothing to do with jumping. It's more just the fact that at this moment in time, it's traveling in a circular path. So I know that in order to maintain that circular path, the net force must be pointing right. Because look at the velocity vector. The velocity vector was pointing this way, then this way, then this way, then this way. So something must have been pushing that velocity vector towards the center of the circle as the ball moved through the path. Does that make sense? There's no questions on that? So I'm going to call this the normal force, F normal. Does anyone know? This is a very difficult question. What equation am I going to write?
F net equals
F net equals M net. There we go. We got it. F net equals M A. So famous. Okay.
all of it. We changed the A to a B squared.
Oh, that's true. Agree with that. We're going to change the A to a V squared over R because it's traveling in a circular path. Okay. How about what am I going to replace net force with? What expression might I write?
Something minus.
Correct. Yes, something.
29.4.
Very good. 29.4 minus the normal force. Everyone okay with that? All right, let's plug in numbers that we know.
29.4.
Yes.
Wow. Good job. The mass is 3. The velocity was 4. The radius was 2. So this is 24, I think.
Yeah.
So a fascinating answer, I think. You get just 5.4?
Yeah.
So it turns out the normal force is just 5.4, which is only like, I mean, yeah, it's what, 20-ish% or something of, about 20% of his usual weight. So do you guys understand that if we increase this number, we can increase this number ever so slightly so that he felt weightless, right? Because what if the centripetal force required just was 29.4? Then there would be no normal force. And then what if we had a situation where, suppose because he was going so fast that like 50 newtons of centripetal force would be needed to keep him in the circular path, what would he do? He'd fly off the ramp because he'd be like, well, all we can get, the only downward force we're capable of getting is 29.4. It can't come from anywhere else. The track can only push him up. That's not going to help. So if we increase this V value, then this number would end up having to be negative. There is a scenario where this could be a negative number. Anyone think of it? Well, it wouldn't be, I mean, I guess it sort of is normal force, but where the force from the track could actually point this way. Well, that's true, yes. If you were going through the dip, that's what we're going to have in the dip. But on like a roller coaster, the wheels might be locked into a track, right? So if the wheel was locked into a track, then the track actually couldn't pull down as it's going over the hump to prevent it from flying off. So, all right, let's compare that to 23. So that's going over a hump. Now let's go through a dip.
My parents won't let me jump in elevators anymore.
Well, when you can stand in dips, it's even just fine.
Yeah, that is also a problem.
Your parents want to want.
Oh, no, they can hold, how much do they say, 3,500 pounds?
That's a real one.
That's what they say the weight capacity is. and I'm pretty sure
3,000?
Jumping is not gonna push over 3,000 pounds.
You never know.
True. 3,000, really?
Well,
I guess that makes
like
sense.
17 people or something?
Well, because like 10 people would be all, I mean, could be up 2,000 pounds. Yeah.
You see a whole bunch of friends scoop where you all jump at once.
Well,
That's how we breathe.
Then you set off like the earthquake sensor, right? And it's like locked in place or something. I don't know.
That would just have to go and fall.
Oh. What are they doing? Senior superlatives? What award did you win, Hannah? Most senioritis? Wow, that's an honor.
Where am I going?
You were about to say idle sound like that, and you were just there.
Well, it was snowing.
Mission Impossible guy gets down.
My hair was full of snow.
Or
Well, no.
Did you win one?
Yeah, it
What'd you win?
was creative.
Nice.
With Sebastian.
I'm just trying to comprehend that. How do I hold? How does that work?
Okay. All right, so 23 is very similar to number 20. The ball has the same mass, it's the same radius, but this time, still a 2 meter radius. It's going 5 meters per second this time. Okay. You guys, it shouldn't take you too long to set this up and solve it. Go ahead and give it a shot. It's a very similar question. This time you should be expecting a large normal force vector because again, the net force has to point towards the center of the path. This path being this circle here. You can draw the whole circle if you want.
This is.
Should be bigger first. Do you get like? I'm not even going to the answer to that was I would have to subtract it and I would.
I think. Oh, that's what I did wrong.
Here's the key difference in this problem is this time, if you think about it, isn't the right side of your equation always going to be a positive number?
Yes.
So you need to make sure that you're choosing. It might not be obvious this is what you're doing, but you are choosing a coordinate system where the positive direction points towards the center of the circle. You're always going to want to do that because you know that your net force is going to be a positive number. So you want to make sure that this number out here is going to be positive. Since we know that F normal is bigger than the gravity vector, then you have to make sure that you're writing it like that. Okay. If you go the other way, you're not going to get the right answer. So
My problem was I did 29.4 plus. That's normal.
plus, that would come up if you were, say you're going around a loop and you're at the top of the loop like this. And so the track pushes you this way and gravity pushes you this way, then you would add those up.
It's
That would
like
equal
the-
mv squared over r.
The string in a circle ones.
Right. So like on question for example, on 28, Carl's on a roller coaster. Good old Carl.
Oh, that's
Okay. Well, I actually told an epic story here. 26 is about Bob on a roller coaster, and then 27 is about Albert, and then 28 is about Carl. So it's really like a sort of a really Games of Thrones like, so many characters, different hero arcs happening simultaneously.
different events. And then
Yeah.
29 is about yourself.
Huh?
Then 29 you're on.
Yeah, that's like an R.L. Stein Goosebumps, like choose your own adventure. Now you are the hero of the story. So- Yeah, he was a really good writer.
Is there like in-depth lore to your problem sets?
Oh yeah.
Do they all line up at the end of the year? Like your forgot it's like friends
all over here.
Yeah, I mean Albert and Bob are they're going through a lot.
Jay Hall extended universe.
Yep. So, what do you end up getting here? 66 points. So, how does the ball feel?
Heavy.
He feels very heavy. He feels more than twice as heavy, right, as he usually does. Okay, so this would be quite fast. So what we'll wrap up with is 25. Hopefully, 25 now has a fairly obvious answer. I want to look at 26 to end the day here. Bob's on a roller coaster. So read that question and ask yourself if it makes sense to you. He brings a scale to the theme park. That's a good flex.
Bob weighs like 220 pounds.
Yeah, that's a normal weight.
Big man.
It's not that big.
That's like twice as much as me.
I'm sure it is. I'm just saying, 220 is like, I'm sure it's above average, but.
Don't look at me like that, Daily. I'm 220.
What is the average? No, no. It's not.
Yeah, I'm imagining that.
This is the ground.
But there was like a graph of like a national average of weight.
220 is like a power running back. You know, it's like an Adrian Peterson maybe.
That is
They gave us all our receivers last year.
Huh?
One of our receivers last. So, that's the last year.
Oh. Bradley's not building an all receiver.
Yeah, but like Julio Jones probably be 220, I'm guessing.
Yeah, right around
Or someone like Calvin Johnson or like, oh, he was a little
Johnson was 6'5", probably like 230, 240.
Okay, but you get the idea. Like any like bigger person to be.
Unless you're Derrick Henry, then you're a freak nature.
How was he like 240? He's a running back though.
Yeah, 250, 6'3", 250.
Like Jerome Bettis was like 275 or something, I think. So. But then like Warwick Dunn was like 170, I think. So it all depends on what your style of play is. But anyway, so 26 says Bob is on a roller coaster before the ride starts. So this is gonna be, man, what a roller coaster this is. Haha, get it? Before the ride starts, his scale reads 980. So this is his force diagram before. By the way, guys, here. Which of these vectors is really the one? Which one of these is the scale reading? The one pointing up. It's very important. A scale tells you how much force the scale is exerting on you. Okay. The scale does not know what your mg value is, really. Now, if you're standing there in equilibrium, it's going to tell you what your mg value is because your mg value gets canceled out by normal force. But the key of this problem is to understand that when he goes around the loop, at the bottom of the loop, right, as he's traveling through this looped path, right, how much gravity is still being exerted on him? Same. The scale doesn't know that. All the scale knows is that I am trying to keep you in this circular path, so I need to exert a heck of a lot of force on you to keep you in that circular path. So when you go to calculate F net equals MA, Well, first, let me back up. Does that setup make sense?
Yeah.
Okay. By the way, Zach already told us the answer pretty much. What is Bob's mass? 100 kilograms, which Zach converted into English, in English weight. It's roughly 220 pounds, but for doing physics, we just say, okay, what this tells us is that Bob's mass must be 100 kilograms. So you can use this reading, this initial reading, to infer his mass, which you're then going to use over here, because what will I replace this F net term with? Is it this minus this, or is it this minus this? It's the first one I said, so this is my positive direction. Up is positive.
What does the F stand for?
Force from the scale.
Oh, okay.
You can call it normal force if you want. Okay, now the V value is 15. And the R was 12. So I replaced the A with V squared over R. I replaced the mass with 100, which I calculated earlier. And there we go. So it's going to turn out that the scale is going to be reading much higher. It's going to tell Bob, oh, right now you weigh a lot more than you did a few minutes ago.
28.
So almost 3 times heavier than
Yeah.
as usual.